Exercise 1. Graph the solution set of the indicated system. Properly graph and label any vertices with exact coordinates. Determine whether the region is concave or convex. Alright, looking over this system, looks like linear inequality, linear inequality, linear inequality. Okay, so this is graphically the intersection of four half planes. Alright, let's see here. We expect to see linear boundaries for this region, and we'd like to at least get these boundary lines that appear in the graph. So what kind of coordinate system will work? Let's consider graphing these boundary lines. This first one, if x is 0, y will be 1. If y is 0, x will be negative 2/3. Okay. This one here is a horizontal line, down low, y equal to negative 4. These two are vertical lines, x equal to 3, x equal to 5. Okay, looks like a fairly simple coordinate system will make this work. Okay, let's label the axes. Let's scale them. 1, 2, 3. 1, 2, 3. Negative 3. Negative 3. Okay, let's get ready to graph the solutions to this first inequality here. Let's see, the boundary line, graph that. Y equal to 3/2 x plus 1. Alright, as we were saying, if x is 0, y is 1. If y is 0, x will be negative 2/3. Okay, when the points are so close together, the line has kind of so-so accuracy. So I think I'd like to actually calculate another point in this line. Now it appears to be going kind of like this, so maybe we'll let x be 4 and see what happens. So here, let x equals to 4 as far as the boundary line goes. We'd have y equal to 3/2 times 4 plus 1. What's that? Cancel, cancel. 2 by 3 is 6 and 1 is 7. Okay, let's get the point 47 on this line. So for that, we can go here to 4, up 7. Okay, this will give us better accuracy. Now, when we go to graph this line, how should we do this? Solid or dashed? This is y less than. This needs to be dashed because the equalities are not solutions to this. Okay, we can label this boundary line with its equation. This is y equals to 3/2 x plus 1. Alright, now, which side of the line to shade? Alright, due to the form of this inequality, with y alone on one side, we can view this, consider just this less than sign as saying below the line, below the boundary line. Okay. Now, the shading is not going to be in some nice blue highlight here because the goal here is to graph the solutions of the system. This is just intermediate step work, so I just kind of use like a pencil, keep track of things as I go. So here's the graph of the solutions of this first inequality, just kind of very roughly. Okay, now let's move on to the next inequality. Contrasting color, red, and the boundary line for this would be y equal to -4, horizontal line, right here. Okay, now, by the way, a solid line because this is greater than or equals to, and we can label its equation here, y equal to -4. Now, as far as the shading of this goes, since this equality is in this nice, easy to read form, we can think of it as being y above the horizontal line here. So now, we're up here so far. So far, it's between here and here is the region so far, but we're only halfway through. Another inequality. Go with another contrasting color. Here, graph the boundary line, the x equals to 3 line. It's a vertical line. In this case, it needs to be a solid line because this is or equals to. The equalities are solutions to this inequality. Okay, x equals 3 is right there. Which side the shade? Well, the inequality reads greater than or equal to. In this case, that can be considered to the right. Okay, now another inequality to graph. Fourth, contrasting color, purple, and the boundary line here is x equals to 5. Also, the boundary line is going to be solid because this inequality is an or equals to variety. Bringing us to here. Okay, now this looks like there's going to be an important vertex up here. We need the graph to go quite a bit up here. And the equation that goes with this boundary line is x equals to 5. The shading that goes with this is to the left, this direction. Okay, now we start to see the overall intersection of all 4 half planes to be right in here. Looks like we need to extend this first boundary line up more. Okay, maybe up there. Alright. Now, let's get the solution set clearly marked off with some shading. Okay, as it's in here, we have like so. Then we also have so. Also. So. And finally. There. Okay. Now, the vertices need to be properly graphed. Okay, this actually takes a little bit of thinking. Now, what about here? Here's this vertex. as it's the intersection of a solid line and a solid line, it indeed belongs in the solution set region. So this will be a solid dot. Okay, how about this vertex? Solid line belongs in the solution set, solid dot. Okay, it's going up here. Now here we have a solid line, but a dashed line. Okay, dashed line. So these points are not part of the solution set here along this line. That excludes this particular line as well. Okay, it's not good enough to be a part of one of the inequalities. It has to satisfy all of them to be in the system solution. And since it's not satisfying the blue line inequality, it's excluded. So this will need to be a hollow circle. Okay, like so. How about up here? Same situation. Dashed line and solid line. This vertex is not part of the solution set. We'll need a hollow circle here as well. Okay, pretty good. Now, besides graphing them properly, we're supposed to provide their coordinates. Alright, let's see how we can do that. This point here, this one's the intersection of a y equals to -4 and an x equal to 3. Alright, not too complicated there. This must be the point then, 3, -4. How about this point? Intersection of x equals to x equals to 5 and y equals to -4. Okay, so clearly this is the point 5, -4. Up here, alright, now we have the intersection of the x equals 5 line and the blue line, whose equation is y equals to 3/2 x plus 1. Okay, it's actually a bit of a system solution here. Again, y equals 3/2. X is now 5 plus 1. Okay, so what are we up to there? 15/2 and one more, 17/2. That would be 8.5. Does that make graphic sense? Let's see here. It's 3, 4, 5, 6, 7, 8.5 is up here. Okay, graphically reasonable anyway. So let's label that. That's the 5, 17/2. Okay, this point here, x equals 3 intersecting with y equals 3/2 x plus 1. Alright, y equals 3/2 times 3 plus 1. Is that 9/2 plus 1? 11/2. So 5.5. Does it look about right? Up here, here's 5, 6 in here. Yeah, that looks pretty good. Okay, so let's give the coordinates of this vertex as being 3, 11/2, we said. Okay, now we've got our solution set, well, shaded, but wait, it should get labeled here. So right in here we could say solution set. Right here. Okay. And one more remaining issue. Is this region concave or convex? Well, consider any 2 points in this region. The line segment connecting them would also lie in the region as well. So the region is then convex by definition. Alright, now one other thing. Maybe we should be checking this over a little bit. We haven't actually done that. Okay, let's take a point that is clearly in the shaded region. For instance, let's see, 4, 4, 1. How about that? 4, 1. So here goes our check. 4, 1 is in the shaded region. Okay, what's it mean to be in the shaded region? That means it's a solution to the system. Okay, so then we should be able to substitute it into each inequality. And we're supposed to get true statements every single time. Here we go. First inequality, y, 1. How about less than 3/2 times x is 4 plus 1. Let's see, this side becomes 6 and 1, 7. 1 less than 7, true. Second inequality, y, okay, y is 1. How about that being greater than or equal to negative 4? True. Think of the real number line when you're doing this sometimes, because it's easy to get confused, even though it's a simple matter with negatives, numbers running around. Okay, third inequality, x greater than or equal to 3. X is now 4. 4 greater than or equal to 3, true. Lastly, x less than 5. X is currently 4, less than or equal to 5, true. Okay, there's a check of some sort anyway. So now, looks like this question's complete and likely correct. Exercise 3. Graph the solution set of the indicated system. Properly graph and label any vertices with exact coordinates. Determine whether the region is concave or convex. Alright, looking over this system, looks like this is a linear inequality. The graph will be a half plane. This is a linear inequality. Its graph will be a half plane. So we have the intersection of two half planes here. We're expecting a region to have linear boundaries at the very least. Okay, let's think about getting these boundary lines graphed. Each one will be a straight line. To get a coordinate system that at least fits these boundary lines, let's consider, say, the intercepts. If x is 0 for the first one, imagine this is an equality momentarily. If x is 0, y is negative 3. If y is 0, x is 6/4 or 3/2, 1.5. Okay. For the second one, when we graph the boundary, which is the corresponding equality here, if y is 0, x will be 4. If x is 0, y will be 4. Alright, with these kind of intercepts in mind, apparently a simple coordinate system with x-axis negative 5 to positive 5, y-axis negative 5 to positive 5 will fit everything. Okay, labeling the axes, scaling the axes, 1, 2, 3, 1, 2, 3, negative 3, negative 3. Alright, let's get a contrasting color out and begin to sketch the graph of this first inequality. For the boundary line, if y is 0, x is 3/2, 1.5. That would be about there. Okay, if x is 0, y will be negative 3. It's there. Alright, the boundary line, in this case, needs to be a dashed line because this inequality is strictly less than. The equalities, which are on this line, are not to be solutions. Okay. label with its equation. This is 4x minus 2y equals 6. Now, as far as which side of the line gets the shading for this half plane, we could substitute 0, 0. If we do that, we have 0 less than 6, which is true. So 0, 0 side of the line contains all the solutions. Sort of like temporary shading here with this pencil, because we're really after the graph of the system, not just this one inequality. So we have at least one half plane visible here. Now let's go to the second inequality. New contrasting color, the boundary line. If x is 0, y is 4. If y is 0, x is 4. Okay. The boundary line in this case will need to be solid because or equals to is in this inequality. Could label its equation here. This is y equals to 4 minus x. As far as which side of the line to shade, okay, since this is in the form of y less than mx plus b, we can think of this as saying below the line. Okay, that'd be here. And now, what about the intersection of these two half planes? It's in here. Alright, so this is how we will shade. Come in here. And then up here. Okay. It's a good idea to label the solution set clearly. So right here, solution set. Now, this vertex here is supposed to be properly graphed. So looking at it, we notice this is the intersection of a solid line, points belonging to the solution set, at least up here, but a dashed line here. So this actual vertex here, because of the dashed line here, it does not belong in our solution set here. So we'll need to indicate that by using a hollow circle when we graph this point. For instance, like so. Hollow circle. And let's, however, proceed to find its exact coordinates. For that, we'll need to now solve a system of equations, the blue line and the red line intersecting. This means 4x minus 2y equals 6, intersecting with y equals 4 minus x. Okay, in this case, you could go a couple ways. Maybe you decide to write the second equation in general form or standard form. So 4x minus 2y equals 6, and then x plus y equals 4. Now you can do an elimination method. Add two of these equations to this one, roughly speaking. So 4x and two of these is 2x, is 6x total. Negative 2y and 2y, the y's are eliminated. 6 and 2 of these, that's 6 and 8, that's up to 14. looking like x equals 14 over 6, better known as 7 over 3. Does that make a consistency with the graph? 7/3, 2 1/3. Let's look at the x. Here it is, 1, 2, and 3. Okay, 2 1/3 looks okay. Keep going. We can use the second equation as a source for y. Y equals 2. 4 minus x, x we now know to be 7/3. This will equal, 4 is 12/3. 12 minus 7 over 3. Looking at 5/3. Does that make graphic consistency? Here's 1, 2. Okay, 5/3, 1 and 2/3 in there. Yeah, looks okay. All right, let's record this point then. 7/3, 5/3. Okay, now there's the issue of maybe we made a mistake here. Maybe we try a little something as a check. Okay, let's see here. Here's a simple point. 1, 1. 1, 1 is surely in the shaded region. If we shade it, what does that mean? That means it's a solution of the system. Okay, well, what's it mean to be a solution to the system? This means upon substitution, it should make each inequality a true statement. So, let's try substituting into each inequality. Alright, first one, x is 1. 4 times 1 minus 2 times y is 1. Less than 6. What about this statement? 4 minus 2, that would be 2. 2 less than 6? True. Okay, second inequality, 1 for y, less than or equal to 4 minus 1 is x. 1 less than or equal to 3? True. Okay, give it a check there for likely correctness. Now, one other thing. Is this region concave or convex? Okay, well, consider any 2 points in the region. Any 2 points you consider, the line segment that connects them, the straight line segment that connects them, also lies in this region. Thus, this region is convex. Okay. That completes the question. Exercise 5. Graph the solution set of the indicated system. Properly graph and label any vertices with exact coordinates. Determine whether the region is concave or convex. Okay, looking over this system, it has linear, linear, linear. Okay, all linear inequalities. Alright, so this means we're looking at an intersection of 3 half planes in this case. We're expecting a region that should be convex and have linear boundaries when we're through. Okay, well although it's hard to decide what coordinate system will fit the region, we could at least try to get the boundary lines in sight, and let's consider those. In the first case, the boundary line for this will be the equality version of this inequality, and for instance, when y is 0, x is -1. When x is 0, y will be 1. In the second inequality's case, for its boundary line, when this becomes an equal sign, for the case when x is 0, y will equal 7. Okay. If y is 0, x will be 7 halves. Okay. Third inequality, when we graph this, when we get to the boundary line, letting x being 0, Okay, y is going to be negative 11. And y is 0, x will be, well, 11 fourths. Okay, now that we see a y-intercept up at 7 and at negative 11, that's quite a bit of y-axis. I think we should probably go to a scale of 1 centimeter equals 2 units in order to fit this graph on the paper. Okay, we'll start there. Now the negative 11, alright, let's suppose this is negative 12, so then 10, 8, 6, 4, 2, call this the origin. Okay, I'd like to label the axes. Some scaling. Remember, 2, 4, 6, 8. 2, 4, 6, 8. Negative 4, negative 8. Negative 4, negative 8. Negative 12. Okay. Well, let's get out a contrasting color and start to graph this first inequality. Well, when x is 0, y is 1. So careful, there's 2, 1 right there. When y is 0, x is negative 1. Okay, well, that's about there. Okay, now that we see these 2 points are so close together that this may not be a very accurate line, I feel better if we just go ahead and compute another point. Let's say something out here. Maybe let x equal to 6. Let's see what happens. Okay, so x is 6 here. 6 minus y equals negative 1. Negative y equals negative 7. Y equals 7. Okay, 6, 7 goes on the graph. Let's do that. I'll go here to where we have x is 6. 7, that's 2, 4, 6, 7. There. Okay. Now, what about this boundary line? Because this is greater than dashed line, don't want to have the equality cases be part of the solution set here. Label. This is x minus y equals negative 1. How about shading? Okay. We could test 0, 0 here. Put in 0, 0, 0, 0 on this side, 0. Greater than negative 1? That would be true. Okay, so it looks like we need to be shading 0, 0. It's the side of the line for this. Since it's a system, I'm just using a pencil to keep track of my regions here. It's the solution set of the system that's going to get the dark shading. That's what we're really after here. This is all intermediate stages. Now, next inequality, second contrasting color. Okay, the boundary line. Let x be 0, y is 7. 4, 6, 7. Y is 0, x will be 7 halves. Okay, that's 3.5. Let's see, there's 2, there's 4, there's 3. 3 and 4, halfway between is 3.5. Now, how about graphing this boundary line? This is only greater than. This needs to be a dashed line. Okay, its equation is 2x plus y equals 7. Okay, third inequality, a third contrasting color. Let's get the boundary line. If x were 0, y would be negative 11. Okay, negative 10, negative 12, negative 11 right there. If y is 0, we have x equaling 11 fourths. Okay, that would be, let's see, 2 3/4. So, let's see here. Here's 2, there's 4. Alright, 3's halfway between 2 3/4, about there. Alright. Sketch this line. Let's see, what sort of line are we using here? Or equals to. Okay, now here the equalities are part of the solution of this particular inequality. So its boundary line is solid. Oh, and we forgot to shade the side of the line on the red curve. Let's go back before we proceed forward here. Okay, here we are back to the second inequality. Let's put in 0, 0. 0 greater than 7. False. Okay, so it's the other side of the line that gets the shading as far as this red line goes. That means out here. Okay, now let's go on to the one we're presently working with. First of all, I want to label the boundary line with its equation. That'll be 4x minus y equals to 11. Now, which side of the line gets the shading for the inequality? Substitute 0, 0. 0 less than or equal to 11 is true. It's a 0, 0 side of the line that gets the shading. Okay, where is the common intersection of all three of these half planes? It's inside here, just in this little triangular region. Okay, now we got to shade this. It's rather small. I'm going to use the finer marker, not the broad highlighter, I suppose. There. 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 Okay. Solution set. Okay, now we have some vertices to correctly graph, and for this, I'd like to use this circle template. Now, this vertex here, what should we do about this graph for a good graph? This is a dashed line, this is a solid line. This vertex does not belong in the solution set, so we'll use a hollow circle. Let's see, I think this will do. Okay, and this one here, dashed line, this point is not in the solution set, just a vertex. Hollow circle. How about here? Dashed line, solid line. Alright, to be in the solution set, you must satisfy each inequality. Dashed line means these points are not in the solution set, so this point needs to be a hollow circle as well. Okay, now we're on to getting the coordinates of these points. Maybe we start here with this one we just graphed. It's the intersection of the green line and the red line. Okay, so this involves solving a system of equations in itself. The green line is here, 4x minus y equals to 11. Here's the red line, 2x plus y equals 7. Okay, this actually is a system all ready for elimination. Basically add the equations to each other, and we get 6x here. The y's are eliminated, equals to, that's 18. Alright, so this gives us x equal to 3. Let's make sure this is consistent with the graph before we go further. Out here, yeah, the x-coordinate does look about like 3. Okay, let's keep going. We can get the x from the second equation. We'd have y equal to 7 minus 2 times x is now 3. That will be 1. How's that look graphically? Here, yeah, that's about 1. Alright, so now we can label this with 3, 1 for the coordinates. Okay, let's go up here to this vertex. Now we need the green line and the blue line to intersect. Okay, the green line, the equation for it is 4x minus y equals 11. The blue line, the equation for that is x minus y equals negative 1. Okay, we've got a chance to do an elimination here. We can take the first equation minus the second from it. That will eliminate the y's. Okay, 4x minus x, 3x. Negative y, subtract negative y, 0 y's. 11, subtract negative 1, 12. Okay, the result here then is x equals 4. Is this consistent graphically? Yeah, that looks like about x equal to 4. Let's keep going. We could use this second equation as a source for y. We would have initially maybe negative y equaling negative 1 minus x, which is 4. So this puts a negative 5 on this side, meaning then that y equals 5, so we think. Check this out graphically. Up here, yeah, okay, here's 4, we're up above, 5 seems reasonable, looks alright. Okay, so 4, 5. Okay, let's go to this vertex, label its coordinates. Okay, we need the red line and the blue line to intersect. The red line equation, 2x plus y equals 7. The blue line equation is the x minus y equals negative 1. This is ready for elimination format here. Add the equations together. Y will be eliminated. 2x and x, 3x equals 7 and negative 1. That's 6. So it looks like this would give us x equals to 2. How's that look graphically? Here, yeah, x about 2 looks alright. We could use this second equation as a source for y. Y would equal 7 minus 2 times x is 2 now. That gives us 7 minus 4, or 3. How's that look graphically? 3, yeah, about there looks good. Okay, 2, 3. Coordinates for that vertex. Alright, now, how about checking this out, checking this over here? Maybe we make a mistake, kind of complicated region here. Okay, let's see what to do. Let's try to find a point that's clearly in our region. Now it's a small region, and the scaling is 1 centimeter is 2 units. Okay, let's sort of shop in the middle of the region more or less, see what we can do. Okay, now it looks like here's 2, there's 3. So I'm going to come to 3 on the x-axis. If I go up 1.5 centimeters, I feel I'm certainly in this region, and that would be a matter of saying then 3 and then 3. Okay, so it looks like almost certain 3, 3 is in the shaded region. What's it mean to be in the shaded region? Don't forget the fundamental things. This means that 3, 3 is a solution to the system. Okay, so what we have in mind is, let's try substituting it into the original, into each inequality. So substituting into each inequality. Let's examine that. what's got to happen? We need to have true statements every single case. Okay, looking at the first inequality, we need to have 3 for x minus 3 for y. That's going to be greater than negative 1. This gives us 0 greater than negative 1. That's true. Think of the number line. 0's to the right. Okay. Second inequality. 2x, 2 by 3, plus y is 3, greater than 7. 6, 9. 9 greater than 7, true. Okay. Third inequality. 4 times x minus y is 3. How about that being less than or equal to 11? 12 minus 3. Okay, we're down to 9. 9 less than or equal to 11, true. Okay, there we are. At least that point really does appear to really belong in the solution set, and there's our check there. Now, the last remaining part of this question, determine whether the region is convex or concave. Okay, it's a triangle. Well, pick any 2 points you like in this region. The line segment connecting them would also lie in the region. So we also have the conclusion then that the region is convex. Okay, that completes the problem. Exercise number 7. In graphic terms, what does it mean to solve a system of 3 linear inequalities? Okay, well, let's think of one linear inequality graphically. The solution set is a half plane. When you're solving a system, you're seeking the intersection of the individual graphs in your system. Now, in this case, this describes a system of 3 linear inequalities. All right. According to what we've said so far, then, we could claim that graphically, this would mean we are finding the intersection of 3 half planes. So find the intersection of 3, because there's 3 linear inequalities, half planes. Okay.